We start at the beginning.
Okay.
As a child, were you good at mathematics? Like, was mathematics a natural thing for you?
Yeah, it was very natural. And I always liked it. I liked counting. I liked continually multiplying things by 2, although by the time I got to 1,024 or whatever it is, I had enough of it. But I liked math. I discovered as a very young kid, maybe 4, something called Zeno's paradox. Did you ever hear of Zeno's paradox? My father told me that the car could run out of gas. And I was disturbed by that notion. It never occurred to me. But then I thought, well, it shouldn't run out. It could always use half of what it has, and then it could use half of that, and then half of that, and it could go on forever, and so it would never run out. So now, it didn't occur to me, yes, but it wouldn't get very far either. But the idea that, in principle, you didn't have to run out of gas was kind of a profound thought for a very little boy.
Did it feel like this was where your career was going to take you, or were you like another boy who dreamed of being a baseballer or something?
Oh, no. The only thing I thought about was I would be a mathematician, whatever exactly that meant. I didn't know quite what it meant, except that mathematics was the only subject I really liked.
You were something of a mathematical phenom. You had already taught at Harvard and MIT at a young age. And then the NSA came calling. What was that about?
Well, the NSA didn't exactly, that's the National Security Agency. It didn't exactly come calling. They had an operation in Princeton where they hired mathematicians to attack secret codes and stuff like that. And I knew that existed. And it had a very good policy because you could do half your time at your own mathematics and at least half your time working on their stuff. And they paid a lot. So that was an irresistible pull. So I went there. Actually, in the middle of my mathematics career, which ended when I was about 37 or 38, was that I spent 4 years at a place called the Institute for Defense Analyses down in Princeton, which was a super secret government-based, National Security Agency-based place for code cracking. But I also learned about computers and algorithms, and I did one thing there that was quite good, because I can't tell you what it was, it's all classified. So I had a good career there, both doing mathematics and learning about the fun of computer modeling.
Stepped up your mathematical career. And you started working with this man here. Who is this?
Oh, Chern. Yeah, Chern was one of the great mathematicians of the century. I had known him when I was a graduate student, actually, at Berkeley. And I had some ideas, and I brought them to him, and he liked them. And together, we did this work, which you can easily see up there. There it is. And
it led to you publishing a famous paper together. Can you explain at all what that work was?
No.
Oh. Well, I'll tell you what, can you explain this?
I could explain it to somebody, but...
well, how about explaining this?
But not many people.
I think you told me it had something to do with spheres. So let's start here.
Well, it did, but I'll say about that work, it did have something to do with that. But before we get to that, that work was good mathematics. I was very happy with it. So was Chern. It even started a little subfield that's now flourishing. But more interestingly, it happened to apply to physics, something we knew nothing about. At least I knew nothing about physics, and I don't think Chern knew a heck of a lot. And about 10 years after the paper came out, a guy named Ed Witten in Princeton started applying it to string theory, and people in Russia started applying it to what's called condensed matter. And today, those things in there called Chern-Simons invariants spread through a lot of physics, and it was amazing. We didn't know any physics. It never occurred to me that it would be applied to physics. But that's the thing about mathematics. You never know where it's going to go.
But this is So incredible. So we've been talking about how evolution shapes human minds that may or may not perceive the truth. Somehow you come up with a mathematical theory, not knowing any physics, discover 2 decades later that it's being applied to profoundly describe the actual physical world.
Yeah.
How can that happen?
God knows. Yeah, but there was a famous physicist named Wigner, and he wrote an essay on the unreasonable effectiveness of mathematics. So somehow this mathematics, which is rooted in the real world in some sense, we learn to count and measure, that's kind of, everyone would do that. And then it flourishes on its own. But so often it comes back to save the day. General relativity is an example. Minkowski had this geometry, and Einstein realized, hey, it's the very thing in which I can cast general relativity. So you never know, and so it is a mystery. It is a mystery.
Okay, so that's at least given us a flavor of that amazing mind in there. Let's talk about Renaissance, because you took that amazing mind, and having been a co-cracker at the NSA, you started to become a co-cracker of the financial industry. I think you probably didn't buy efficient market theory, and somehow you found a way of creating these astonishing returns over 2 decades. I think the way it's been explained to me, what's remarkable about what you did was that it wasn't just the size of the returns, it was that you took them with surprisingly low volatility and risk compared with other hedge funds. So how on earth did you do this, Jim?
Well, I did it by assembling a wonderful group of people. When I started doing trading, I had gotten a little tired of mathematics. I was in my late 30s, I had a little money, I started trading, and it went very well. I made quite a lot of money with pure luck. I mean, I think it was pure luck. It certainly wasn't mathematical modeling. But in looking at the data, after a while, I realized, hey, looks like there's some structure here. And I hired a few mathematicians, and we started trying to make some models. Just the kind of thing we did back at IDA. You design an algorithm, you test it out on a computer, does it work, doesn't it work, and so on.
So can we take a look at this? Because I mean, here's a typical graph of some commodity or whatever. I mean, I look at that and I say that's just a random up and down walk, maybe a slight upward trend over that whole period of time. How on earth could you look at that and see something that wasn't just random?
It turns out in the old days, and this is kind of a graph from the old days, commodities or currencies had a tendency to trend. Not necessarily the very light trend you see here, but trending in periods. And if you decided, okay, I'm going to predict today by the average move in the past 20 days, there's 20 days, maybe that would be a good prediction and I'd make some money. And in fact, years ago, such a system would work. Not beautifully, but it would work. So you'd make money, you'd lose money, you'd make money, but this is a year's worth of days, and you'd make a little money during that period. But it was a very vestigial system.
So you would test a bunch of different sort of lengths of trends in time and see whether, for example, a 10-day trend or a 15-day trend was predictive of what happened next?
Sure. You would try all those things and see what worked best. But the trend following would have been great in the 60s, and it was sort of okay in the 70s. By the 80s, it wasn't such a
It didn't, because everyone could see
other
that.
people did it.
So what happened? So how did you stay ahead of the pack then?
Well, we stayed ahead of the pack by finding other approaches and shorter-term approaches to some extent. But the real thing was to gather a tremendous amount of data, and we had to get it by hand in the early days. We went down to the Federal Reserve and copied interest rate histories and stuff like that because it didn't exist on computers. We got a lot of data and very smart people, and that was the key. I didn't really know how to hire people to do fundamental trading. I had hired a few. Some made money, some didn't make money. I couldn't make a business out of that, but I did know how to hire scientists because I have some taste in that department. And so that's what we did. And gradually these models got better and better and better and better.
I mean, I think you're credited with doing something remarkable at Renaissance, which is building this culture or this group of people who weren't just hired guns who could be lured away by money. Their motivation was doing exciting mathematics and science.
Well, I hope that might be true, but some of it was money.
They made a lot of money.
I can't say that no one came because of the money. I think a lot of them came because of the money, but they also came because it would be fun.
What role did machine learning play in all this?
Well, in a certain sense, what we did was machine learning. You look at a lot of data and you try to simulate different predictive schemes until you get better and better at it. It doesn't necessarily feed back on itself the way we did things.